everyone, welcome to this online-only CocoaHeadsNL meetup. Thank you all for being here tonight. For the people that are new to CocoaHeadsNL, we are a monthly meetup group for Apple developers. We are part of the international CocoaHeads and talk about anything Apple related. First of all, we'd like to thank our regular sponsors. They make it possible for us to host our meetups and to record and stream them as well. We also like to point you to our apparel shop at cocoaheads.nl/shop. If you buy any of these products, you help us to host these meetups. Today, we will be giving away 2 JetBrains licenses for any of their products. If you win, you get to choose which one. The license is valid for a full year. You can enter the raffle by simply entering the Meetups channel on the CocoaHeadsNL Slack at cocoaheadsnl.slack.com. If you don't have access to it yet, you can use this invite link. Today, Manuel will share his ideas about reducing complexity in our code, so we can create easily extendable and maintainable systems. We hope you'll enjoy this talk. Please keep an eye on our Meetup page and our social media channels for updates on next month's Meetup. If you don't want to miss any of our videos, please subscribe to our YouTube channel. It's the easiest way to see every video that we publish. But we also have our own tvOS app where we will publish every video. We hope everyone stays safe and healthy. I now hand it over to Manuel.
Hey, I'm Manuel, and I want to make a plea for a more mind-sized software design. I've worked in many different companies and positions over the last 12 years with a focus on iOS development. In that time, I've always worked with companies that would call themselves agile, with teams that would describe themselves as agile, that would practice some agile methodology, but it never was agile. Because agility is not some methodology, some framework, or some certification. Agility is the ability to respond to changes fast. Agility is a sports term. Agility is a physics term, and yeah. So let's not certification industry steal it. If it doesn't feel agile, it ain't agile. Simple as that. So why do we need agility? Changes can be forced upon us at any time. Changes in our business markets, in the strategic decision making of our company, technological reasons, or laws might be changed, and we need to adapt to that fast. Maybe we just have a few days or weeks to fulfill a certain law. If we design software with agility in mind, the design should not get in the way when it comes to the other tools that we use in our agile processes. Also, it should support CI/CD workflows. So, guys, we need to be better at that. And we should maintain this agility at any time, and not only now and maybe a few months and releases down the road, but not after that. No, during the whole life cycle of an app, from being supported in the App Store till being not supported in the App Store. And of course, agility should be done in respect to inter-team processes, so that also other teams or team members, non-programming team members, can benefit from our increased agility as well. Oh yeah, my positive feedback loop. Yeah, I do think that if we do start doing things better, then everything gets better. But yeah, well, probably another discussion, also a very sensitive topic. So yeah, why is scaling so hard? I mean, I've not met one person who says, yeah, that's we are agile and it's great, and no. Well, I think because scaling is hard. Scaling knowledge work and scientific work is hard, and that's what programming is. If programming would be easily scalable, computer would be doing it. Simple as that. Because then it also would be easily automatable, but it isn't. And I want to illustrate, if our team would be of the size 1, the time to complete a project would be the time that it would take one person to code it. Well, makes sense. Quite logical, not sure. But many people assume from that point on scaling would behave like that you just divide the time that one person would need to finish the job by the number in the team, by the by the number of teammates. But it just doesn't work that way. Why? Well, I'm not the first person that tries to illustrate this. So on the left, we see a formula that I call the Kevlin-Henney conjecture, because I do know this through Kevlin-Henney. Not sure if he came up with it, but if he did not, I guess he would have named it somehow. But yeah, so this describes I think pretty well how scaling teams works in reality, and I want to explain why. So again, we have T1, and now we are, after that we have this term in square brackets that is actually Amdahl's law, which describes how parallelization works, because you will always have an offset during parallelization, and this is expressed like this. And the second term after the plus sign is communication overhead times all the combination of connections between team members. And I think it describes very well. And on the right, I try to illustrate this. So besides the yellow stuff that is the work, we also have this Turkish turquoise color that represents the communication overhead, and we also see the connections. They are not complete, but we also see connections in the orange areas. So there are dependencies of the in the work. So not everything is parallelizable. So I try to illustrate it like this. So it becomes clear it is not simply adding more people and expecting that it will work. I've added this term P plus K equals 1 myself to express that I want to look at the relationship between the portion that is parallelizable in work and the communication overhead, because I think it's quite clear that if your code is not very parallelizable, you will have a lot of team sessions about it. You will have a lot of pairing sessions where you try to reason about the code with colleagues. So this is all this communication overhead. If we would plot it, it would look like this. So the y-axis shows the time that it would need that would be needed to complete the project, and the x-axis shows the number of programmers in this project. And this is overall project. So what we see is that there is a certain point, here indicated by red, where the curve turns around, and this means that actually by adding more people to the project from that point on, the project will more likely be more inefficient. So it will slow down. So by adding people, you effectively slow down the project. And red is this point of no return. And you should not use this formula to make any decision. It is just for illustrative purposes only. There are too much things going on in the real world that this could really express what's going on in a real team, but it's just the idea of complexity that it illustrates. But if we plug in some of the values, we will actually see what I think is a very scary scaling behavior, because if 90% of the work would actually be scalable, which is a lot, I think, by this formula, a third developer would already effectively slow down the project. And if you would have 10 times more, if you can parallelize 10 times more, which is expressed in the second line, you only should assign at maximum 4 developers to that. And I mean, this is a huge gap. And to illustrate, in the third line, the third row shows that even if only 1 promille would not be parallelizable, then you could assign 10 developers. But I mean, that's, I don't know what code base would look like that. So this row could actually indicate that team sizes of 10 are just not sensible in any situation. And maybe some structuring would be in place. But I've also plugged in some very bad numbers. So and it's quite interesting that here I have not truncated the numbers, but rounded to the first decimal place to show that this conjecture actually would say that even the first developer would already be beyond the red point. So such a project of a parallelizable code of 20% or 10% or 1 per mil, as we see there, they are not viable, not in teams. But I do think that many projects that I've seen in my career are in that range. At least that is 20%. So and throwing manpower on that will only slow it down. That's the issue. But throwing manpower on it is the common reaction. But let's also talk about the architecture metaphor. So this is a slide why I dare to give this presentation this clickbaity title. I've noticed in several of my jobs that there is a danger in overstressing the architecture metaphor, and you can see I did not point out where the architecture metaphor might be a good one. In this table, I point out where it breaks, and I think we need to think about another name or another way of explaining what software architecture is. Because I've learned, especially since I started freelancing, that people think that architecture is something that they have to pay extra and that it's not really needed, but and that is something that is done beforehand and then executed and then doesn't contribute to the investment anymore. And I mean, that's just not the case for software architecture. So yeah, I want to point out that where it breaks, and that I think we should give it a more appropriate name, and which in my opinion would be if we would talk about coding strategy, because a strategy is very abstract at the beginning, and so people cannot overstress this. Well, yeah, and we know that strategy can be very different things. It can be a military strategy, it can be a political strategy, economic strategy. So yeah, people are used to this, and yeah. So instead of architecture, I want to talk about intrinsic design, and I do believe, and I do believe that what you see now on the screen is the design underlying every interactive app. The user interacts with the user interface, which triggers the logic to recompute state, and the new state is represented in the UI. It doesn't matter if we are coding in functional programming, structural programming, logic programming, or object-oriented programming. The underlying intrinsic design is always this, and therefore I do believe that everything that diverges from this intrinsic design must be considered additional complexity, and if this doesn't serve any purpose, it must be considered accidental complexity. And this is something, and accidental complexity is what we want to avoid, because accidental complexity is what creates bugs, because it's something that is not designed, it's something that is not really under our control. It's where the bugs live, I used to say, and we want to minimize it. I don't want to say at any cost. That's not the right choice of wording, but I think we should design apps that makes it hard to develop accidental complexity. Any code that doesn't express the intent of the app's designers, so I do not mean user interface designers, but all people that are involved in creating the app, if it doesn't express their intent, and I also do believe that we have a lot of source codes. We are very bad at removing codes. We are afraid, even though we have it under source control, we are afraid of removing codes. We are afraid that we hurt people's feelings when we remove codes that we do not find useful anymore. and also a lot of dead codes. And one thing I also want to talk about a little bit is what I call band-aids here. These are things that were introduced to cope with flaws in the language designs. And these are, for example, everything to do with visibility of things, of visibility levels, and for example, it might be a keyword that is introduced, like final open. I think everybody knows that a class that would be final from default would be much better. But instead, we have to finalize them, or other way around on APIs. And patterns are band-aids, because when we look closely at patterns, then their sole purpose is to deal with the fact that classes, which are the main tool used in modern object-oriented programming, don't have a concept of output. So you cannot just return something from a class like you can from a function. Instead, you have to implement certain patterns to cope with this missing feature of a class, and we have developed many patterns to do so. And I think patterns are cool. They are fun. It's always great when you learn something new, but they also tend to make the code very fragile, because not everybody understands every pattern in the same way or is aware of them, and so it's also a tremendous training amount to teach patterns to teams. So let's have a closer look at classes. So classes are certainly the most versatile types we have at our disposal. They are mutable, they offer inheritance, and they offer any number of inputs, because I can implement any number of methods and setter or whatever. We've talked about how outputs and patterns relate to each other. But I want to point out that any of the above points mean complexity, and if it's something we don't need in a given situation, then it's accidental complexity, and it might work for you, and this might not be a problem for you in the presence, but this extra surface area might lead to deterioration in the future, and maybe just because some experienced guy is in vacation. Classes are pretty much unconstrained, as we've seen, but we know that good software design is about good constraining. We know it for structured programming, which actually was we know it for structured programming, where actually the article "Go to consider it harmful" can be seen as the starting point of a formalized version of that. Functional programming is actually was actually invented to constrain mutability, and for similar reasons, OO programming was invented by constraining visibility. Functional programming uses a global state but immutable one, while OO uses mutable state but hidden one. So it's two solutions to the same problem, mutable global state. It's about constraining. But we learn classes should not take central roles in our designs because they are too powerful. Because with great power comes great responsibilities, and when we put human irrationality into the mix, well, it can be tricky, and this is why we see code bases deteriorate, why we see our agile processes not working. The base is just not given. So another look at the class in comparison to a function. What I want to say with this one-to-one is that in a function, you call a function once and it will return once, while with object orientation, I actually should not call that. Yeah, well, we are looking at a class here. While in object orientation and with classes, we usually have an end-to-end message sending pattern. I mean, we have very different, in different languages, we have very different ideas what message sending is, and I think a lot of languages actually do not get it very well, but usually object orientation is defined as message sending, and there we have an end-to-end relationship, meaning a message sent from one object to another does not have to invoke a response, while it can also invoke more than one response. Think downloading progress, something like that. Yeah. So we actually want this communication pattern that we know from object orientation, but we also want to be as mutable as possible, and we also want to be as constrained as possible. So we want to have handrails, we want to have tracks that we can move on, which we would be better suited with a function, but a function does have the wrong relationship for request and response. So what's the solution? The solution is actually something that in at least related terms is researched since the 1890s, so predates object orientation and functional programming by a lot, I guess. Because this is actually related to currying. Currying is, in mathematics, is the act of splitting up multi-parameter functions into multiple functions with one parameter each. And partially applied functions are very similar in that regard, in that that you have a similar structure and you call those functions to different points in time. And yeah, so what we see here is a function create to-do list feature, and it takes an output parameter as an input, as a parameter, and it returns an input. So input and output are basically the same function type. We just use different names here to indicate the semantics, that once we want to use it as an input and once we expect it to be an output. I will not go into this much deeper at this point. I want to show you some code later and then I will cover this. So let's add this partially applied function to the mix, and we actually see that we now got what we wanted. So in the architecture that I will show you in a bit, I will use this construct to create the module type feature that I will show you in a bit. So yeah, Core UI is the name of the architecture. Its interface is actually a command interpreter, which means that on the top level, the surface area is only a function call that you can perform. Core UI has strict unidirectional data flow, which is very helpful to keep code reasonable, so to keep it mind size. As in every good architecture, the UI is really treated as an I/O device, so there is no other connection between the UI and the rest of the app than message sending. The different parts do not know anything from each other. They are truly separated. And in Core UI, everything is a module. And what I mean by this is that we have at maximum one input, at maximum one output, and we have and every module in Core UI has a DSL. Modules might share a DSL, which allows them to exchange messages, while others have their own DSL system. As in this case, it supports separation of concern and true black boxing, and which also leads to a lot less necessary unit tests. Core UI is based on use case, which is not something I invented, but is introduced by Robert C. Martin in his clean architecture. So if you Google for it, use case clean architecture, you will find a lot of implementations in any useful language, and a lot of documentation. This is a very well understood pattern. Yeah. So this is the overview of a Core UI app. The top is the app core. We see really close by the UI. The next level is are the features, and then the first rectangle layer are the use cases, and the use cases in Robert C. Martin's design use something called gateway, and call stack and store are such gateways, and yeah. So let's have a walk through where I want to demonstrate how information flows through this app. So in this case, an event is fired from the user interface. It's handed over to the app core. The app core level only does one thing: forward any message it receives to every receiver and feature it's now. The UI is a receiver, and the features I've explained you. So the message that comes from the UI first is sent back to the UI, and then it is sent to every of the features. If a feature recognizes the message, it will react accordingly and most likely create a request for a use case, and when a use case is finished, it will trigger sometime later the response. But I want to mention that a feature might use several use cases to finish one message, to respond to one message. But we will keep it with a simple case here. So the start call use case signals via a response that the call is started. The calling feature then creates a new message, hence it's over to the app core. App core again will inform the UI, and then every feature and the circle is completed. So we went from the user interface triggers event to the logic processes a new state, to the new state is represented in the UI. So it is pretty much exactly the intrinsic app design. Now I want to give you a little demo. So this is the app I want to show you. It is a simple to-do app. You can enter to-do, you can tag them, and a simple journaling is kept. So let's enter a to-do. Buy beer. Okay, we can also my computer is a little slow. It's a 5 or 6 year old machine, and the simulator sometimes wants to be a little bit odd because of this. So we can add a to-do date. We want to have beer for the weekend, so let's go shopping on Thursday. Okay, it knows a little bit more, but I think this is enough as a presentation. So now let's implement a feature request from our product owner. So the feature request is that we want to make a to-do item forkable, so that you can take an older one and say fork it, and you have a copy of that. And then a second requirement, we also want to be able to pass in changes, so that we can fork it, but we can change, for example, the title while we fork it, and everything else is forked as it is. I am not the fastest typer, so I have prepared everything as in Git. Okay, now I'm checking out the next commit, and this commit should contain the basic specs for our forking. So what is a spec? A spec is a kind of test, and in this commit I've added this forking test. So let's try to run it, and of course it should fail. Yeah, so of course these tests do not work, because our to-do item, our to-do item doesn't know anything about forking yet. So this is our to-do item. It is a truly 100% immutable data type, and the way I achieve this is by reprocessing the data, by recreating the data for every change that needs to be reflected in this alter methods. which are fed by with this change enum with change enum values with these ones. So you can change the text, the completion date, and the completion status and the due date. The other values here are not cannot be changed by the user at this point. So now let's implement it, and of course I've also prepared that because I'm really not the fastest typer. And I want to point out the changes. So we have added a change case fork here, and we have added it's down here that if it is fork and it comes with assigned changes, then a new item is created with a new ID. So that makes it a separate, distinct object, while the rest stays the same. And then we call alter with on it with the changes that might have been passed in. So of course the list also can be empty. And also in this private alter function, we deal with the changes. So for example, if it is a fork, then we always pass we always return the changed item. But if it is equal for all the content in it, and the change that we just have applied have not changed anything, we actually decide not to return the changed item, but the self item. But that's an implementation detail. Yeah. So maybe we have a look at the test, how we can use those. So here we have the to-do item spec, and here we create a to-do item, and these are tests written with the frameworks Quick and Nimble. And if you're not if you don't know them, have a look at them. It's a great project. I really love to work with this setup. Shout out. So the way it works is that the tests, which are actually inside these it closures, are executed in isolation, meaning that for each test, all the layers above are called independently. So, and the tests are actually the names are concatenated. So this test full name is actually to-do item underscore some underscores. I will forget about the underscores. So to-do item, altering check item, changes completed. So check item means I check it to be completed. And on the right side here we have what we expect. So we expect that the new completed value should be different to the original one. But ID, text, and everything else should not change. I want to. So that's how these tests works. But I actually want to point out how we use this alter function here. So it's just that we. On the original to-do item, call alter, and then we can hand over any change that we want to see reflected, and it will return the new value. Yeah, and now we have added the forking, so we can also inspect that. So spec, it's not only a test, it's a spec, so you can inspect stuff. So here, for example, we can also see that the alter method can take a variable list of values. It could also be invoked with an array. So now let's have a deeper look at the forking specs that I've just applied. So first we create a new original to work on. We see that we can apply several changes at once. And now we fork it with no changes, and we expect it to have a different idea, but the rest gonna stay the same. So let's run the test as we have applied the git command, the last git commit. So we see that all tests have run successfully. We actually have 176 tests. So of course, with all these small tests, it's also very easy to write a lot of tests. And I mean, many of this it closures here you could copy and paste. Well, that's what I did. So yeah, it's also great to have a lot of confidence in your tests. And I also want to point out that you should not look at your test coverage so much, but I want to point out that with this coding style it is easy to get a lot of test coverage very fast. And I think that is a valid metric, not the test coverage itself. It doesn't matter. It's not important that you have a very huge test coverage, but it's very good if you can reach a huge test coverage very fast. And with this architecture, it's very, very easy. So let's go back to the to-do item implementation itself. Where is it? So now that we have seen forking in the test in action, let's see the implementation. So we have this alter function here. If it's invoked with a fork change, then we will actually immediately return the changed item. And if it's not a fork, then we will check if it's if the contents are the same, because we actually don't want to return the new item in that case. Forking itself works like this, that a new to-do item is created with a new UUID, but with the self's text and other data points. And if there are changes, they are applied to this to-do item immediately by calling alter on it. So if the list is empty, nothing will happen. This is pretty much everything that we have to do outside, that we have to do in the state. The store will handle everything automatically. So now we want to connect the user interface to it. So what we need is that we need to have a fork message. So our message is to do fork item with and fork model. So which describes the stuff as a model. So we want to separate the message enums from all other DSLs. So we could be tempted to just exchange the information that we have for forking at different places already, but I introduce a model here because then we have a much clearer separation, and it's also much easier to implement certain protocols. So this is the message that we have to send to indicate a forking. Now we need our to-do list feature to react to this fork message. So we do this down here, and we call the use case, the fork to do item use case request method with a request with a request fork. Fork item with a list of changes, and here again we have the full implementation with an interactor class. Again, everything is totally black boxed, and if we request the interactor to fork, it will actually do so in here by altering the item, and in this switch we translate the model that we have introduced, the fork model, to the appropriate DSL values. Then we change the store by adding the item to it, and then the use case responds to its feature by informing it that the item was forked indeed. Which actually means that we will end up in this place where the response is once again checked, and now it's translated to a message that all the that the user interface and all the features do understand. And we also write a journal entry by triggering a message to do that, but I won't walk you through that. It works pretty much the same. So now the only thing that is missing is the user interface, which ironically we already have implemented somehow, because in the user interface we do exactly the same as we do in the tests. So that's why they are specifications. So let's already compile the new version of the app to make and look at the code at once. The user interface is connected via a view state. It's for SwiftUI, so it uses this observable object implementation. It does nothing special. It processes any new state it receives. And informs the user interface through this published items. So let's look at the implementation. So we have a list of to-do item cells here, and the to-do item cell is implemented in this file. And now the forking is implemented if, yeah, let's look at it. So now our context menu also has a fork submenu. And now we want to remind ourselves for a week later that we want to buy beer, but we want to buy beer urgently. So first we give it another title, and now we change the due date. Or we change the title, or we fork with a new due date. So pretty much as we would expect. How does it look in code? Here we have the context menu. If we want to change the date without forking the value, the item, we do this. So we say it's not forking, and if we want to change the due date for a forked to-do item, then we say yes, it's forking, and we want to present the date sheet as in the other way. So the date sheet is then presented over here, and depending on if it's forking or not, we send out to do fork item with the change, or to do send the message to do change due to this other value for this certain item. And we do very similar for the text changes. So with very little changes. So let's, yeah, no, I did not prepare that. It were really only a few lines of code that we changed, and pretty much only additive code. We created new value for the user because, well, they requested it, now they can do it. And it's been done. Yeah, I mean, I am not a Swift UI expert, so I did have to figure it out. But if I were a little more experienced in Swift UI, I could have written this addition in a mere 10 or 15, 20 minutes. And you will encounter a lot of use cases in this scope. Other will be a little bit more effort, but I do believe that in usual terms, use cases will require less than a day to be implemented. Yeah, we have talked about model and state. also the store. The funny thing about the store is that although it acts a little bit like a class object, it actually isn't neither a class nor a struct. And I want to show you what it is. So I decided to go also here a little bit out of the ordinary, and I must say that after using this pattern in 3 apps by now, I am very happy with it because it's just simple. So what we see here is the declaration for the store. Usually you would go to a class for a store. It's you need a reference type, so struct wouldn't work, and yeah, certainly a class would be the go-to type. But for the same reasons, I didn't want to have a class in the central of my architecture. I also didn't want to use it for a store, so I came up with this construct. Store is a tuple of functions, 5 functions being access, change, reset, callback, and destroy. And store is the composition of those functions bind together in a tuple. Is it tuple or tuple? I never know. So so this is just a declaration. This is something that we definitely need to implement. So how would it look like? Here we have a create disk store function that implements this tuple for usage on a persistent store, storing disk, for example. So again, so this we have this function that returns the store. The store is this tuple, and in place we implement the functions. We say, well, state just returns state. Remember, in single statements function, you don't need to use return anymore if you return. So this function returns the state. So it's just the access of the current state. The change function applies changes that it received by forwarding it to the state, which is then written to this variable. So this is the only place in the app core where we need mutability. So this declaration and these 3 statements for change, reset, and update are the only mutable statements in apps, in my app core, so in the features, in the use cases, and in the state and model. So yeah, so it's very powerful, yet if you get used to it, it's also very simple. Well, then it's persisted to store and so on, and the private implementations for the store persisting, for persisting the store, destroying the store, and loading the store are found down here. So they are not accessible anywhere else. So this is the only interface we have to create this store. To create another store, you could just implement another function and maybe have a core data store. If you notice closely, I said it has to be a reference type. so that it can be passed around. Yet, if you do now a little bit more of Swift, you might be aware that a tuple is actually not a reference type, it's a value type. But that's actually the reason why we use function on the top level here, because they are reference types. So when they are passed around, it's still the same function. Yeah. So this maybe we should also talk shortly about this callback. So callback is a function that takes another function as an input parameter, and this is useful for this, because this is now a very, very simplistic notification pattern. It's a listener pattern, so that the store, every time it gets updated, will inform all its listeners. So it's very simplistic. We do not, even for such a pattern, we do not necessarily need classes. So in this case, we do not even need structs. So yeah. Again, there is no underlying level here, so everything is known to us. We know everything. We own everything of the implementation. We own our code with such a implementation. While classes, they're difficult. We've talked about it. So, as I said, one reason why I started thinking about doing things differently and try this route was that I wanted to have something that is easily usable in any kind of agile as in process, surroundings and environments. And I want to show you this feature map, which is a real project I've completed with this architecture, and I hope that this demonstrates that. Yeah, let me explain you. So at the top we see user, call, chat. These are the features in our app. In the next row we see the use cases, and in the first column we see our sprints. So it's a sprint planning tool, and in the area between those rows and columns, we see what I call actions here. So mostly the user interactions with which we would trigger the use cases. So now the idea is that usually a use case has one action, sometimes two, because sometimes you do the same thing from different places in the user interface. But usually you have one action for one use case, and the idea is that a use case is always so small that it can be done in one day. Usually even much faster. Sometimes you will need more time than a day, especially if you want to implement some new algorithm. But my proposal at this point is, with this kind of architecture, with agility built into the architecture, you can actually ditch a lot of the baroque-esque stuff we have in our processes. So the idea is if a use case in average does not exceed 1 day, you simply count the use cases and you can predict when you will be done. So you count the use cases or the actions, and the actions will be even implemented even faster because they are usually just one call in the user interface, but they represent the use cases. So yeah, so the idea, what I want to show you is that the agility of the code flows back into our processes. Yeah, but I also guess you have to try it out. So let's see if I have missed some of those key facts. Yeah, the app core is fixed or static actually, which means that once it's created at app time, it doesn't change in any way. It stays the same till the app is ended. Also, model and state are immutable. I've shown you that. So the idea is that if something cannot change, it also cannot change unintentionally. So there's a whole category of crashes and bugs that you cannot have in your code if you apply this kind of coding style. And a customer once told me that he had asked a professional testing company to evaluate his app, and they replied that and in the end report they pointed out that it might have been the first app that they've tested that didn't show a single crash. So yes, immutability, go for it, really. Okay, also want to mention again, you should go for a unidirectional flow in your app. It doesn't matter if you want to implement my architecture or another one. Unidirectional flow always helps you to keep code under control because it becomes much more reasonable. This also means forget about singleton, please. I want to mention, I have not demonstrated it, but it was one of the first things I discovered with this architecture. I want to mention that the UI is swappable. You might want to do it for different reasons. You want to maintain you want to support alt devices with a different UI. You want to migrate, or you want to actually implement different features, because what I discovered is that it's quite easy to implement, to use the same app core for different features. Example, I've implemented an app core that just spits out random stuff, and I've created 4 different apps with it, all exact same app core, but different UIs. And one app is a role game dice app. One app does the same, but on the command line, so Mac command line, so much more nerdy. But there's also an Apple Watch app that lets you flip coins or use an 8-ball or whatever these things are called in case you are bad at decision making. So the apps are very different, but they use the same core. I want to point out that that my architecture is something that I dare to call fractal, because it is using the same pattern everywhere, the same module pattern. which also results in very similar syntax, as you can see. The first line shows how to change a to-do item. The second, how to add a to-do item to an app state. The third shows how to do the same thing, but on a store. And the fourth shows a call to add a to-do item as it would be sent from the UI. You have seen UI with Swift UI, but UIKit is also quite easily implementable with some notifications. Reach out for me if you want to have more codes on that. Yeah, and you've seen the simple test, and here I want to point out, with this level of testing, with this confidence, we can build up confidence. So the tests that you write for a to-do item are very similar to a test that you write for a use case or for a feature or even for the complete app core. And so you can build with the same skill set, you can build up from the model over the state and store to the use cases and features and app. You can build up confidence, which makes it, I just can say it feels like a little bit more like a mathematical proving to me than other unit testing. You build up, you can start axioms, the models, and from there you can build up your confidence to prove like state. This has been my presentation. I know it's been a lot. And it's also have been the first time for me to talk to a monitor without any live audience. I just have aquarium over there, but they had been very mute. No reaction from them. So if you want to reach out to me, you will find all the information you need at this address. You will find also my blog there. I have a few articles there regarding this architecture, also about immutable data types in Swift. You will see some kind of journaling there, which I didn't show here. I hope a few people stay around with questions and remarks. Otherwise, have a nice day and see you soon. Hey everybody, and thanks for watching. I don't know if there are any questions or maybe some suggestions on what we could talk now. I definitely would like to get some feedback on this and your thoughts. So so any remarks, any comments? Would you guys could consider something like this to use in your projects? Okay, Bart, you are asking for the difference between spec and the test, and simply put, there's none. Technical speaking, there's no difference, just that in this framework setting with quick and nimble, it's more like coming from the BDD style, where tests are also meant to describe the system and what has been completed in the programming and something like that to the product owner, customer, whatever. Yes, exactly, Bruno. Exactly. Any other question? Okay, there are some things I had not the time to answer or to describe, mostly because I'm using too much as you can hear in my presentation. But I also want to point out that something that I did not really mention is that this code also is pretty much completely declarative in opposition to being imperative, what most codes in Swift probably are today. I have an article written about this that is focused on this aspect, on the declarative part. It's on Medium. It's called Fully Declarative Swift for Real-World Projects. So if you would like to check it out, it would make me very grateful. Yeah, and I would also be happy for any later feedback, and if you want to get in touch with me, do it wherever you can find me, maybe on the Slack server, the CocoaHeadsNL Slack server. Yeah, so yeah, shall we end it?